All right, I think I want to wrap up this discussion on channel estimation with a very quick discussion of what you could call the bias-variance trade-off, which is a way of understanding and analyzing channel estimation and the key trade-offs that are involved in that. So let's just start with looking at the problem. So let's just imagine again we're looking at a single symbol, say in time or in frequency, and we have some true channel h of n, and we get some noisy values, say from a raw channel estimate. I'm going to denote as before those estimates as h at naught of n, which are the true values plus some noise. And they're only available on some subcarriers, which are indexed I. And just as before, we do some kernel estimate to smooth and interpolate out those raw values. And that's found by weighting those raw values over the ones that are the subcarriers that are available, and then normalizing those values with the z naught. Now, if you have this, let's define what we say is the mean squared error of this estimate, which is a very natural metric to look at for the error. And that'll just be the average value of the difference between the estimate and the true value. And that will be in general a function of the subcarrier location. And the expectation here is over the randomness in the noise. For now, I'm just going to assume that the h of n is deterministic. And it might also sometimes called the normalized MSE, which is the mean squared error divided by the value of the channel, so kind of like a fractional error. Okay, so we want to figure out how what is this MSE and how we try to minimize it. All right, to analyze the MSE, the key idea is to look at the error, which is the difference between the true and the estimate, h hat. Now, the key thing is that h hat is linear in the raw values h of 0. So we can break up that error as a function of two terms. One, which was dependent on the signal, and the signal meaning the h minus the h hat, which is itself the functions of the other h hat of h of k's. The second is the terms depending on the noise, which I'll call v of k. All right, and so that is just the component of h hat here, which is from the noise. So you have a signal component and a noise component. Now it turns out once you do this decomposition, this mean squared error will be a sum of two terms, which is the squared of the signal component plus the variance of this v. Now the reason why that's the case is if you want to look at e of en squared, it will be a deterministic value because this is non-random because it only has non-random components in it. And this is a variance term here. And the zero mean term here, so e of en squared will be es squared plus the expected value of ev squared. Note that es is completely deterministic. So it's a sum of these two terms. And these two terms are called the bias squared and the variance squared, which I will explain in a moment. All right, so first let's look at the variance error term of that mean squared error. So the variance error comes from this component, which is basically the kernel regression when you just apply noise to it, vk. So that's what we get here. Now, remember that the variance of each one of these terms will be the original variance divided by the signal power that was available in the reference signal. So it's n0 divided by ex. Now, with that, you get this very important formula that the variance is given by this expression here. And I'll show you some examples to understand where this formula comes in. But let's just show you why this is the case. This is easy because, first of all, remember that ev squared is just this. But each of vk's are uncorrelated. So when you look at the expected value of the numerator here, you will just get the squared value of each of these components times the expected value of ev squared because they're uncorrelated and zero mean. And the denominator is completely deterministic, so you'll just get that value squared on this. But remember, the denominator is just the sum of these vk's. So when you plug this expression in here and you plug this expression into here, you get this. So this is where we get this formula from. Now, to understand that formula, let's take a look at a very simple case, which is what you could call a uniform kernel. So imagine I do this. I have a kernel, which is a length L on one side and L on the other side. So it has a total of 2L plus 1 values in it. And it'll just be 1 if in this region and 0 otherwise. So basically the kernel regression in this case is just averaging over all the samples that are in this window. Now, suppose there are k of these reference symbols that happen to land up in this window here. In that case, we can easily work out the variance, and it's just as follows. We apply that expression, so it'll be a sum of the w of n minus k's here squared, but there will be exactly k of them, and each one will be 1, so the numerator will be k. And the denominator, you'll also get k, but you square it, so you get a k squared. And the k and k squared cancel out, and you get n0 divided by ex divided by k. So the upshot of this is that if you average over k values uniformly, the variance error goes down by a factor of k. So all that math is to show you that if you want to reduce the variance error, you want to make that window as large as possible, or more importantly, to grab as many reference signals as possible. And it's roughly scales with a factor of 1 over k is about the number that you can grab. So to reduce the variance error, we want very wide kernels. All right, now let's look at the bias error. So the bias error, remember, that is from the signal component, and it's the true signal minus this value here. But we can rewrite this as just kind of as h minus h bar, where h bar is given by this expression, and where these alphas are given here. Now, what's the impact of this? Well, this just tells you, you can see here that these alphas always sum to 1 because of the numerator. You just look at the numerator and denominator here. And it means then that h bar of n is kind of an average of values of hk, where k is close to n. So you're kind of taking a local average. Now, because of that, you're looking at how then different is h of n from a local average h bar. Now, what you would expect then is really how large that window is relative to the rate of variation of that h of k. So just to make that more concrete, imagine I had considered two kernels. One is a very narrow kernel like this, and one is a very fat kernel like this. If the kernel is very narrow, it's only going to grab samples very close to the sample of interest. And if that's very narrow relative to how fast the channel changes, for example, if this is in frequency, where that kernel width is much smaller than the coherence bandwidth, we would expect this ES to be small. On the other hand, if we have a very fat kernel like this, the channel is varying considerably over that region in which we're averaging, so we would expect that the bias error to be large. And this will occur when the kernel width is greater than or equal to the coherence bandwidth. So the upshot of this is that if you want the bias error to be small, you want to have the kernel, the width to be very small. Or in other words, increasing the kernel size will increase the bias error. And this here we can see that there's a trade-off. What I've done is I've taken an example realization of a channel in blue, and I added noise to a bunch of reference symbols, and then I looked at the estimate for different kernel widths, sigma 2, 7, and 25. When you take a very low kernel size, you have a very high variance error because you're averaging over a very small number of samples. But you do have a very low bias error because your width of the kernel is very short relative to the variation of the channel. In this case, you get a very noisy estimate like this, but on average, it's correct, but it has a lot of noise here. On the other extreme, if you take a very fat kernel, you smooth out all that noise, but you get this kernel here which basically doesn't follow the actual shape, because in some sense it's biasing the estimate towards something that's much smoother than the actual channel is. And somewhere in between here is kind of more, you'd get kind of the best minimum error here. So on the left side, you have small kernel, you have a high variance error. On the right side, you have a very wide kernel and it's a very high bias error. Now, another way to think about this is the following. I could look at the mean squared error as a function of that width, and you see you get this kind of bowl-shaped curve like this. If you have a very narrow kernel, you'll introduce a lot of variance error and it goes up. On the other hand, if you introduce a very wide kernel, you introduce a very high bias error. And somewhere between these two, there's an optimal value. And that optimal value will depend on the rate of variation of the coherence bandwidth and the noise. Just to give you an example here, interestingly, we got an optimal value around 9. And in this case here, the mean delay spread was about 200 nanoseconds. And that means the coherence bandwidth is roughly about 1 over 2 times that, so about 2.5 megahertz. 9 subcarriers in this case would correspond to about 135 kilohertz, all right, which is, you can see here, that is taking a value that's quite a bit smaller than the coherence bandwidth. It's not trying to push it up close to this because it doesn't want to introduce too much bias error. All right, there's an interesting effect of bias and variance error when we look at the final performance of the system. All right, to understand this, let's just take as an example, I have a channel estimation error, which I can model as following. H hat is the true channel plus some variance V. And this V will have both the components to the bias squared and the variance. All right, now let's take a look at how both of these bias squared and variance terms scale to understand their effect in the final system performance. The bias error is generally going to scale with the channel power. The reason is that it's really related to the angular dispersion of the channels or the delay dispersion of the channel. If you were to increase the transmit power, all of those parameters will just scale up linearly because it's a linear medium. So you can imagine that the bias squared term is going to be some constant times the power on the channel. All right, and this constant here will increase with the kernel width. So if you have a very wide kernel, we'll expect that the CB to be larger, and if you have a small kernel, we'll expect CB to be smaller. Now, in terms of the variance term, we would imagine that the variance term will scale with this inverse of N0 over EX. For example, we saw that if you average over K samples, this term CV would be 1 over K. So if you have a wide, it's roughly equal to 1 over the number of reference symbols over which you're averaging. Now this term CV, on the other hand, will decrease. With the more averaging you do, it'll decrease with the kernel width. So we have the CV and CB and CV. Now let's look at the effect of this when we actually apply this noisy channel estimate into equalization. We'll see a very interesting effect, way to understand bias and variance from a communication perspective. So here's our channel. We have R is equal to, let's just say on a sound symbol, Hx plus some noise, and that noise variance is N0, and the signal energy is Ex. Remember in this case that if we knew the channel perfectly, the SNR would just be Ex times H squared divided by N0. Let's call that value gamma naught. Now, here's a simple model for the channel estimation error that we had, which is Hx is to H plus V, and that variance is a sum of two terms, as we said, the bias squared term, which is scaling with H squared, and the variance squared term, which is scaling with N0 over Ex. Now, imagine I take that channel estimate and I do my equalization by taking the conjugate of H hat multiplied by this. So I just take that H hat, I put it in, which is H plus V, I put it into here, and for R, I put that into here, and when I add these through, I get the following. For the X term, I have an H squared X term here, and then I have this effective noise term, which is a sum of these two terms here, that H plus V times W and V times Hx. If we neglect this product of two terms, which hopefully is small, we'll get that this noise is a sum of two terms. One coming from this H star VW, that is coming from the original noise, and the second is coming from the distortion related to the channel estimation error. So I've just written that here. So we'll call this total noise the effective noise. Now, let's take a look at the effective signal-to-noise ratio that you get when you introduce the channel estimation error. we have our H star, we have our Z, which is our equalized symbol, which is a complex conjugate of the estimated channel times R. And we saw here that it's a sum, as before, of the signal power squared times the signal plus this noise term, and the noise has these two components. Now let's take a look at the effective signal-to-noise ratio. Let's take a look at the relative power of these two terms. The signal energy will be from this, which will be an h to the fourth times the value of x squared, which is ex, so that's our signal energy. But the noise will be a sum of two components. One is the variance of this term, which will be scaled with h squared times the n0. And the other will be the variance of this term, which will have an h squared times the square root of ex, the square root of x, which is ex, and then the variance of v, which is nv. But if we remember that nv is the sum itself of these two terms, we get this very interesting expression for this effective signal-to-noise ratio, or what you could call the signal-to-noise and distortion ratio, because it includes both the noise and the distortion from the channel estimation error. Just before we visualize this, let me just prove how you get this expression. All you do is you just take our expression for ES and divide it by N naught, so put both of these expressions in, and then if you divide here out the h squared terms, and then you divide by n0, you will get this resulting expression after you substitute in here. So you'll get this. Now, let's take a look at this, the effect of this effective signal-to-noise and distortion ratio. Here's our expression from the previous slide. And what I've done to visualize this, I've done the following. I've taken our S and R and dB and plotted on the x-axis, and I've plotted two lines on the y-axis. The first line, which is the blue line, is just the S and R, or equivalently, it's the S and R you would get if there was no channel estimation error. On the red line is the S and R that you would get with this distortion, or the SNDR. That is this. So I plotted gamma versus gamma naught. Of course, the signal-to-noise and distortion ratio is always a little lower because, of course, I'm adding extra noise from the distortion. But there's two interesting regimes to think about. The first regime is what you could call the low SNR regime. And in the low SNR regime, this term, the CB times gamma naught, becomes small. And then you just get gamma naught divided by 1 plus CV. So what you see here in this low SNR regime is that the effective signal-to-noise and distortion ratio decreases, the distortion effectively decreases the SNR by this factor 1 plus 1 over CV. In other words, this CV, remember, is coming from the variance error. So at the low noise regime, you're getting a penalty from the variance error. In other words, if you want to make the performance small, gap loss here small, you want to average over a large number of terms. For example, if CV was 1, this would be drop it by 3 dB, meaning if you just averaged over one symbol. But if you averaged over, say, 10 symbols, CV would be about 0.1, and you'd be going over 1 divided by 1.1, which is a loss of a little less than 1 dB. Right, so this part here is limited by the variance error. Now let's look at the other extreme, which is the high SNR. When gamma naught goes to infinity, you can see here that it just saturates off in this regime. And that happens because if I take gamma to infinity, this basically limits to 1 over CB. And in other words, what happens is that even if you have no noise, you get eventually just limited by the bias error in your system, because you're just making a fundamental assumption about the channel, which is not exactly correct, and it saturates. Now, this is interesting then. There are two regimes that this distortion you can look at. In the low SNR regime, you're limited by the variance error. So if you want to make the variance error small, again, you have to have a very wide kernel. And if you're in the high SNR regime, you're limited by the bias error. And in that case, you want the kernel to be very narrow. Right? And this shows you the trade-off and has a very nice way to think about bias and variance from their effect in a communication system. And this will depend on which regime your system is operating in. Let me just wrap up with then trying to estimate the effective noise in practice. So this is a very useful graph if you want to try to evaluate a system if you've actually built it to see how the channel estimation performs, and in fact, this is what you will do in the lab. So remember that when you have equalization or LR, we need to actually estimate not just the channel, but we also have to estimate the noise. So let's figure out how to do that. So usually the noise can be estimated by looking at the residual error. So what happens in this case, if I have some residual reference symbols, which are the received symbols times channel estimate plus noise, and then I can get some channel estimate. So what I could do is come up with an effective noise estimate by just looking at the difference between the received symbol and the estimated channel times x of n. All right, and then I take that average. All right, this term here will have, in some sense, both the noise and the distortion, because remember that if I take the Rn and substitute it in here, I'll have a term which is related to the noise, and it will have a term that's related to the channel estimation error, so it captures both. The problem, though, is that the residual error will be biased. I won't have the chance to go into the math of this, but because you're actually measuring the residual error on the same symbols on which you fit the model, you actually slightly overfit a bit of that noise. So the variance component of that error will be slightly underestimated, and the amount of it's underestimated depends on how many symbols you're averaging. But it will actually capture the bias error typically correctly. So if you wanted to be really precise, you could actually compensate this error in reality by scaling it up a little bit to account for the fact that it underestimates the noise. But if you're averaging over a large number of symbols, this error shouldn't be too large. And I'll show you how large it is in practice. Now, if you wanted to find an unbiased estimate for the effect of noise, you could do the following. So we realize that the error is coming biased because you're using the same symbols in which you trained your estimator for the error estimation. One of the principles in machine learning, if you take a machine learning class, is that if you want an unbiased estimate, you get a different set of symbols to actually measure the error. So what you could do is the following. Suppose I could find another set of test symbols, which I did not use for channel estimation. And I basically do the exact same calculation for the error, and I just take the received symbols minus that channel estimate, how well it performs on this. In this case, you can see here that you can show that this will be an unbiased estimate for the noise, so it will actually give you a more accurate value. Of course, you don't want to generally do this in reality, because this would add even more reference symbols and overhead into your system. You would have some reference symbols used for channel estimation, and then you take that and separately use a separate set of estimates for the noise estimation, and that would be excessive overhead. But it's extremely useful for testing your system in either a test situation or in simulation. So what you can do, for example, is you populate the data symbols with known symbols, and then you try to look at this test error to see how well it performs. Of course, to do this, you have to know what the data symbols are, so it's only valid in the regime where it has a test. But this is a very good test to do when you're building a receiver to try to estimate its performance. And this is exactly what you will do, in fact, in your lab. Now, just to illustrate this, the true versus estimated value errors, what I've done in this graph is the following. I took a channel with some delay spread here and put a number of reference symbols in this case, and I measured the true error by looking at the average noise on the data symbols. Because this is simulation, I know what the true data symbols are used, were sent, and these were not used in training, meaning they were not used in the channel estimation. And then I can see here the estimated error, which is the estimated noise measured on the reference symbols. So a couple of points here. We see it's pretty accurate, and for this particular case, it's off by about a dB. And as I said before, this estimated value, where you estimate it on the reference symbols, is going to be a little bit optimistic. It's off by about a dB, but it becomes lower as you get to higher SNRs, and that's because the error in this regime here is dominated by the variance error, which it underpredicts, but in this regime is dominated by the bias error, which it's actually correct. All right, if you go to the demo you will see an actual graph, which is very useful to get. So what I did in this case, in the demo, I increased the SNR, and for each SNR value, I measured the signal to noise and distortion ratio. And indeed, you see this kind of performance that we predicted from that theory, where there's a small gap at the low SNR regime. And that small gap is around only about 0.4 dB. And if you have a saturation SNR here of about 27 dB. So this is pretty good performance. What you're getting is with a very simple channel estimator, you're only losing about 0.4 dB in the low SNR regime. And you're getting up to about 27 dB here. Since most wireless systems typically don't need greater SNR than that, this saturation SNR is not a problem at all. So this is actually pretty close to what you would get in a real commercial design. Usually a commercial design, you try to get that channel estimation error within about, in the low SNR regime, within about 1/4 to 1/2 dB. So you're seeing that here, and this is definitely respectable. So what we have end-to-end with some very simple techniques, you've been able to build a simple channel estimator, a channel estimation error, which is very practical to build, and it gives really very respectable performance, and you have a way, I think, I hope, of understanding that performance by looking at this bias and variance trade-off. So once you've done all this, you can go through the demos. I just want you to do one simple exercise, which is to look at the bit error rate performance, all right, over different SNRs. One case where you have a true channel, that's in blue, and the other is in orange, which is with the estimated channel. And you'll see that for low SNRs, there's just a small gap. It's barely visible on this graph, and that's just because you're limited by the variance error. But eventually, the SNR saturates, so even as you increase the SNR, in this case, the bit error rate is saturated with the channel estimation error. And this is very typical of what you will actually see in a real system. So go ahead and do this lab, and then once you finish this lab, you can once you finish this in-class exercise, you can go ahead and do the lab, which you'll actually look at a more complete downlink channel, downlink 5G NR PDSAH demodulation, and so at that point you'll actually be able to transmit and receive with a real channel estimate of a full downlink PDSAH transmission. And after that, we'll go on to the next topic, which is on beam forming.